We'll now discuss some of the results of angles and different types of angles and their interiors. My first result, if I have two rays u and v that are concurrent with a ray h and lie on the same side of the line containing h, then I have either the betweenness relation HUV or HVU. We're going to let h be the half plane containing u and v, with the obvious exception of the endpoint that actually lies on my ray h. We're then going to let h1 and h2 be the two half planes that are determined by the line containing my ray u. We know that h has to be in one half plane and h prime has to be in the other, so we're going to say h is in h1, h prime is in h2. And if that's not accurate, just switch the labelings on those half planes so that it is. And we're going to let w be a point on the interior of ray v. Since h is the half plane containing v, w must be in h. So we know w is in h and it has to be in either h1 or h2. So it's either in h intersect h1 or in h intersect h2. If we're in the first case, if w is in h intersect h1, well, h intersect h1 is by definition the interior of angle HU. So by axiom 10, we have HVU. If W is in H intersect H2, that is the definition of the interior of angle H prime U, which gives us H prime VU, once again by axiom 10. So that means that H prime V plus VU is equal to H prime U, or by the linear pair theorem, I could rewrite this as 180 minus HV plus VU is equal to 180 minus HU. So rewriting that equation gives us HU plus VU is equal to HV, which by definition means I have the betweenness relation HUV. The next thing we're going to talk about is perpendicular. So we say two lines are going to be perpendicular if they intersect and form four right angles at their intersection point. We can say rays or segments are perpendicular if the lines containing them are perpendicular. So our next theorem is going to be our criteria for perpendicularity. If we know we have the betweenness relation ABC, and D is any point not on our line AB, then we say lines DB and AC are perpendicular if and only if the measure of DBA is equal to the measure of DBC. So I went ahead and drew a picture here and labeled some things to help make our proof a little bit easier. So let's start by assuming that our two angles are equal. DBA is angle 1 and DBC is angle 2. So we'll assume these are equal, and then we'll prove that the two lines are perpendicular. Since these are supplementary angles, we have that the measure of angle 1 plus the measure of angle 2 is 180. And since angle 1 and angle 2 are congruent, we have that this is the same thing as 2 times the measure of angle 1. Dividing both sides by 2 gives us that angle 1 is 90 degrees. We then have angle 2 is also 90 degrees since they're equal. And then our bottom two angles will also have to be 90 degrees since they are vertical angles of angles 1 and 2. So we do have all four right angles. Now let's actually suppose that these two lines are perpendicular. By definition of perpendicular, that means these two angles are each equal to 90 degrees. So I have the measure of angle 1 is equal to the measure of angle 2, which is exactly what I needed. The next theorem I'll look at is known as the crossbar theorem. The crossbar theorem says, let angle BAC be a non-degenerate non-straight angle. B and C are interior points of its sides. And if D belongs to the interior of this angle, where the distance between A and D is less than alpha, then the ray AD meets segment BC at an interior point E. While I won't directly prove this, I will draw a picture demonstrating what's going on. So I have this angle BAC. B and C are interior points of the sides, and D belongs to the interior of the angle. I want to draw my ray AD. And if I draw the segment between B and C, then the idea is that this ray must intersect this line segment at some point E. The last one I'll look at here is going to be the ray-point duality theorem. The ray-point duality theorem says, suppose I have concurrent rays, H, U, and K, and I know these rays intersect a line L at interior points A, B, and C, where L does not pass through my point of concurrency. It doesn't pass through the vertex here. Then I have the betweenness relation HUK if and only if I have the betweenness relation ABC. So the ray-point duality theorem essentially gives me a relationship between my betweenness of my rays and my betweenness of my points. And I won't prove this here, but if we look at a picture and maybe draw a few other pictures, it seems to make sense that this seems to work.